The goal of this video is to understand and apply action-reaction interactions as explained by Newton's third law. Newton's third law can be stated as follows. If object 1 exerts a force onto object 2, then object 2 must exert a force onto object 1. These two forces will be equal in magnitude but opposite in direction. If we call the force that 1 exerts on 2 an action, then we refer to the force 2 exerts on 1 as a reaction. Thus, Newton's third law is often stated as for every action, there is an equal and opposite reaction. This should agree with your own experience. If you push against a wall, you feel the wall pushing back against you. If you do this in a low-friction environment, you can fully expect to receive a backward acceleration. This simple idea applies equally well to rockets. A space shuttle takes off by strongly pushing gases downward. The gas responds by pressing just as hard on the space shuttle upward. This also explains why the net force in Newton's second law refers only to external forces acting on a system. These three masses are connected by rigid rods. When a force from the outside is applied onto mass 1, it in turn pushes mass 2, which in turn pushes mass 3. Newton's third law says that because mass 1 pushes on mass 2 has to push back on mass 1. And because mass 2 pushes on mass 3 will push back on mass 2. Of course, mass 1 will also push back against whatever external thing is pushing it, but because that force is not acting on this system of masses, we can't include it in the net force acting on the masses. Newton's third law says that these action-reaction pairs are equal and opposite, so these two forces will cancel each other out in the net force equation, as will these two forces, leaving us with a net force equal only to the external force acting on the system. Note that the forces canceling each other out are acting on two different objects. Newton's third law refers to at least two different forces acting on two different objects. This means that these masses cannot accelerate themselves. Any force mass 2 exerts on mass 1 or 3 will be reciprocated in kind, meaning the whole system will stay at rest until a force acts on it from the outside. If a system cannot accelerate itself, you might be wondering how a car is able to drive down the road. The engine of the car applies forces to spin the wheels, but both the wheels and the engine are part of the same system, so there has to be something else at play, something not part of the car. The tires of the car press against the road, so the road responds by pressing against the car. This accelerates the car down the road. If it starts to rain, it becomes more difficult to grip and push on the road, so the forces are reduced. It becomes harder to accelerate your car. In a low-friction environment, it becomes extremely difficult to move the car at all, even though the tires will continue to spin just fine. The force does not have to be a contact force. Because the Earth exerts a gravitational force onto the Moon must exert the same gravitational force onto the Earth. It's important to note that these two forces will have exactly the same magnitude. Consider as an example a baseball as it flies through midair. Baseballs have a standard mass of 0.145 kilograms, and since it's close to the Earth, we can safely assert that the acceleration it experiences due to gravity will be about 9.81 meters per second. This corresponds to a gravitational force of about 1.4 newtons. Because this force comes from the Earth, there must be a reaction force acting on the Earth. Since the magnitude of the force on the ball is about 1.4 newtons, the Earth will experience exactly the same force. However, while the ball is accelerated quite significantly from this force, the Earth has a much larger mass than the baseball. Plugging in the force and mass of the Earth into Newton's second law reveals that the ball accelerates the Earth toward it at an order of 10 to the minus 25th meters per second. Assuming this acceleration is constant throughout the flight of the ball, and choosing a relatively long hang time of 7 seconds, we find that the ball displaces the Earth by only an order of 10 to the 25th meters, substantially smaller than even the width of a single atom.